Okay, well, here's where we left off and where I said I would start up again too, just for repetition's sake. We're trying to demonstrate really two things: the facility of this parameter rho prime, twice the size parameter, and then the function of the index refraction, the so-called Lorentz term. And also we're demonstrating the behavior for spheres of the forward scattering when normalized by the Rayleigh scattering for the same sphere. And a range of refractive indices, which means that to vary for any constant refractive index, to vary rho prime, we had to change the radius. That's what we did. These are all me calculations, me code. And see this crossover right around rho prime equals 1. That's the key thing. Rho prime is going to tell you whether you're in the Rayleigh regime, right, less than 1, or whether you better pull out the me equations when you're greater than 1. But we get this nice universality. Everybody lines up together with the rho prime parameter. Last time I alluded to the fact that there's a rho, the phase shift parameter. It's been around for years. It's, again, 2kr, but then just m minus 1. And so they're approximately equal. I think one's about 2/3 as big as the other, but they're slightly different functions with the refractive index. That shows up, the nice universal behavior over here, everybody going right into 1 when we multiply by rho prime squared. Isn't so with rho. It jumps around by a factor of 3. Now, it's worth rewriting this or redrawing this over here. One could then take this result and say, well, okay, what is the intensity doing not as a function of rho prime? I mean, you guys want to know what it's doing as a function of r or d, right? So we can do that. What it's saying is that if we plot this, say, as a function of d equals 2r, early on, small rho prime can very much, with any reasonable index refraction, can be a small size as well, but there's a refractive index dependence. So it's coming up like this, and remember, that's in the Rayleigh regime, right? We're normalizing by the Rayleigh scattering, so now I'm only plotting I naught, so I got to multiply by the Rayleigh scattering. So all these have slopes of 6, radius to the 6th, lambda to the 4th. They've got the Lorentz term. Squared, and so on. So these are all these curves, and the index refraction is increasing in that direction. But somewhere, once again, around lambda as far as size is concerned, but more precisely, somewhere around rho prime equal to 1, these all cross over to a different functionality, which if you take a look, you got a single r in rho, but we're squaring it, right? So we're taking an r to the 6th and dividing it by an r squared, right? That leaves an r to the 4th. So this picks up as r to the 4th and no function of the index refraction. So these come slamming in here. Now there's ripples at the crossover, correct? Ripples that are really quite large, which we can hide on logarithmic plots sometimes, right? You got to be self-effacing on that. So don't forget that there's going to be some sort of ripple structure here. But for each one of these refractive indices, the crossover is pretty much at the same rho. Rho prime equal to 1, equal to 1, equal to 1. Just depending upon what the refractive index is. So that gives you a good feeling. Oh, and then finally, I would be remiss not to remind you that the limit at large rho prime of a sphere, of scattering from a sphere, is circular aperture diffraction, right? So a baseball, for instance, long, deep into that regime, and circular aperture diffraction has I0 of 1/4 k squared r to the 6th, r fourth. I said k to the 4th, didn't I? And I wrote r k to the square, but I've got it right correctly now, okay? So which is circular aperture, I might have misspelled that, diffraction. Okay. So, nice clean description. Any questions? Time's up.
Yeah. I was going to ask about what about the total cross-section? A lot of people care about that.
I'm going to get to the total cross-section. Let's think about it just a little bit, though. Oh my gosh. Touched the wrong buttons and it goes crazy. Let's see. I'll put this down. Remember with the single slit, how we got a width square dependence straight ahead? And we were worried about conserving energy. Of course, as the width got bigger, it got skinnier. Same sort of thing happening here. As that radius gets bigger and bigger, the forward intensity goes up as the fourth power. But let's remember the diffraction angle's going down. Of course, it's only going down linear, isn't it? Right? Lambda over d, lambda over d. But, right, it's a solid angle. So you got a lambda over d and you got a lambda over d, and the area in the forward direction is inversely proportional to n to d squared. And so the d squared and the d to the fourth leads to a d squared dependence ultimately. So energy's in analogy to the single slit. Let's see. Anything else? Okay. Recently, Justin Maum, you might say Will's replacement at Kansas State, who's been doing theory, has managed to generalize the Rayleigh scattering cross-section for any shape. Exactly. So, and much of this behavior applies to any shape. So that's good. Now, the other very complex, very loaded with information slide is this one. So I'll sort of go through it again. This is the phase function. But we've normalized, again, by the Rayleigh cross-section. Here in the forward direction, you can see uniform scattering for this region, falling off now relative to the Rayleigh cross-section with rho prime. The forward scattered intensity, as we just talked about over here, is in fact equal to the Rayleigh cross-section divided by rho prime squared. That's what this was telling us. Okay. Then in the limit, where this really gets big, there's that circular aperture diffraction that I told you about right there. So we understand that forward scatter. Then, of course, we go through one. That's the Gounier regime, written in red and dashed line red here. That's independent of all the machinations of refractive index and size. There's a size measurement there for you. Okay. Now, I've left out some detail. You might miss by 20 or 30% if you do Gounier analysis and don't pay attention to the refractive index. Then again, if you want some measure of size, damn the torpedoes, full speed ahead, right? Ignore the refractive index and get the size. Any number's well conceived is better than no number. And indeed, we've worked out how to convolute in the refractive index to improve this measurement But it's just a lot of detail. We published a paper. I don't want to talk about it today. Subsequently, we start getting these -2s. As rho prime continues to increase, the -2 is really that equal tangent line to the hump from the Gunier. The three-dimensional diffraction starts to becoming quite evident. The hump seems to be centered at the rho prime value. I'll stress again, these are empirical observations. You might recall my first day I said, look, we'll pretend like the me calculator is an observable phenomenon in nature, and we'll systematically observe it and be empirical scientists. And that's what I've done here. So these are, and since we're the first to see the hump, we get to name it. It's the hump, okay? So there we are. And then after the hump, everybody comes close to that original 3D diffraction. And so that's one of the beauties of this thing and of the Q-space analysis, is that you start off with diffraction in 3 dimensions, and you see how the scattering evolves when you start cranking up rho prime, really. You could say index refraction. And so physically, you'd be changing the index refraction, but ultimately, the key parameter isn't the index, it's rho prime. Any questions on that plot? And I say universal. When I publish this stuff, I say quasi-universal because it doesn't work perfectly, right? There's some gaps there, and it's probably a factor of 3. Let's see, I think this is remote. What if the index refraction has an imaginary part? What, in fact, is a significant imaginary part? And we seem to be the first to be able to describe that. We only did it a year or 2 ago. The hump gets messed around with. So let's see here. Lots of information. Let's start here. N plus I kappa will be my notation. And I've done both monodisperse and polydisperse. Remember, polydisperse, just enough dispersion to smudge out the ripples. And let's go over to the polydisperse case, and let's go to the largest size parameter because it's most evident there. So again, you see forward scattering, Gunier, you see the -3 power law due to two-dimensional refraction, and there's the hump. And this is where kappa, right, the imaginary part, times kr, the size parameter is 0. There's the hump. And then as kappa kr starts approaching 1, see here's 3/10, look, the hump's dying. See that? And then at 1, it's pretty much dead, and by the time you hit 3 and 10 and everything else, it's totally gone. So kappa kr of 1 is kind of a transition region. If kappa kr is a heck of a lot less than 1, the hump's there. And if it's a lot more, the hump's totally gone. Question?
At all these kappa krs, is the hump slope still the same as the tangent at the QR1?
QR1.
Is the slope still the tangent?
Oh, with respect to the Rayleigh to Bygons?
Yeah.
Well, no, when the hump disappears, and it still comes out and touches, let's see, I don't have,
I'm not saying I'm not asking if it's the same tangent line, but is the slope of the tangent still the same as the slope?
no. So this -2 tangent, is that what you're talking about?
Yeah.
Yeah, when the hump disappears, that no longer applies.
Slope changes then?
Well, yeah, see, if we're down here, we still have the Gunier regime in the same place, but this -2 line would be down here. So that definitely is gone. You okay?
I had a slightly different question, but that's not so.
Okay. Well, maybe I'll cover it as I go along. Let me continue the description. We'll see what happens. Notice, however, everybody sort of comes, they all sort of join again here. And remember, that's back when we get close to the original 3D diffraction. So, and the universality now is to notice that I've got 2 orders of magnitude, right, of range here on the size parameter. And in each case, well, certainly in these 2 cases, the hump disappears in the same manner. So to think about this further, this yellow curve where kappa KR equals 1, if the size parameter is 500, that means kappa is 1 over 500. Quite small, actually. On the other hand, for kappa KR to be equal to 1 for KR equals to 50, the same effect, then we're only kappa is 1/50th. The point being, it's not the magnitude of kappa that determines how the system changes. It's the magnitude of the product with the size parameter.
So physically, what is that?
Don't know.
Well,
Well, okay, slow down, yeah, slow down. I wanted to talk about 5. 5, a few things are happening. Notice it's moving around here as we change kappa, but remember, kappa is involved in the Lorentz term. So up there, to get to kappa KR of 1, kappa is going to be a 5th. And you start putting a 5th into M, and it changes the Lorentz term. So I want to alert you to that. Okay? So then, indeed, it's just the magnitude of kappa that's causing problems. But on the other hand, if we get to larger particles, then it's the effect on the hump and not on the Lorentz term. Now, as Will was leading me, what about? What's the physical significance of kappa KR? Well, you can show that the penetration depth of the waves coming into the sphere, the 1 over E length, call it delta, is given by the wavelength in vacuum over 2 pi kappa. Then, of course, if you ratio delta to the radius, you might say the relative depth of the wave probing in, it works out to be exactly 1 over kappa KR. So that we hadn't anticipated that. Here again, we were being empirical scientists. We stumbled upon this observation, and now it has a reasonable interpretation. So let's repeat. If kappa KR is 0, this ratio is infinite, and the light is illuminating the sphere just like it would under any me situation. If with kappa KR is 3/10, the inverse of that is 3. That means that the penetration depth is still 3 times the radius, so there's some attenuation in here, and sure enough, we're starting to see effect. But by the time we get to 1 and 3, then of course, like 3, then we've only penetrated 1/3 of the radius or so. We've got something that looks like this. Any bigger kappa KR, what the heck, it's still confined to the front surface, and there's no change.
so it's like if I have a big glass ball, the scattering is that from something that's dark.
Yeah.
Just there at the end.
Yeah. And here again, I want to stress, so you'll see people looking at minerals. Feldspar might have an index of 1.56 plus 0.003. Right? Oh, that's a small. But if your KR is the inverse of 0.003, 300, and you could with windblown dust, then you got a significant kappa KR. That's the thing to be alert for. A summary, general scheme. I don't think I need to talk about this anymore because I talked about it so much in the other slide, so I'm going to go on. Here's a value. Let's make sure we can speak both languages, Q space and theta space. Q space over on this side. I did the monodisperse. I still think it's always easier to look at the polydisperse just so we don't get confused by the ripples. And you can see the polydisperse case. To be practical, I'm using diameters instead of any rho primes or any size parameters. So here's 1 to 100 microns. I did put rho prime over here, though, just to keep track. And in fact, this is for water, 1.33 and green light. So there we go. And the first thing you notice is look where 5 degrees is. It's clear out there, and that's what's going on when you do logarithms, right? You stretch out the small angles. If I go over here, 5 degrees is over here, and there's, see those forward scattering regions there? They contain the forward scattering lobe, which we talked about here. They contain the Gounier regime. What the heck, they even contain the two-dimensional diffraction. It's all hidden in that forward scattering plot. You might say, well, crap, they're not, I would say something worse, but I'll keep it somewhat civilized here. Well, crap, that forward scattering isn't important. I'm going to show you a graph here pretty soon that indicates, that proves that half of all the light is scattered in that forward peak. So it is important. Note where 90 degree is. See that? So there's just that little bit that always peaks up at the end. That's this stuff here. This is the rainbow. Well, this is a primary rainbow. There's the primary rainbow, the secondary rainbow. There's Alexander's band, and this is the glory back here. Okay, so all this enhanced backscattering, I'm blowing off with Q-space analysis. I will tell you that the backscattering is on our agenda right now. We're having fun looking at that empirically. Empirically. I'm not solving any Maxwell equations back there. I'm looking at it empirically. Yes. Notice now, 5 degrees to 90 degrees. What's between 5 and 90? The hump. There's the hump. And I can prove it, I think, in the next slide. There we go. So let's go to the largest size. Let's go to 100 microns. Here's kappa Kr of 0. Here's kappa Kr of 3, which, really zapped the hump before. And sure enough, you can see in angle space now, we've killed the hump. We also killed the rainbow and the glory. You see that with all of these, right? Whenever we have significant kappa, the hump's gone. And up here, of course, we start getting to separate because then kappa is starting to affect the Lorentz-Lorentz term again.
So what information are we losing with higher kappa? Like, what is the physical information that's available in all of these things?
Yeah. Okay, let me take a stab at that. I think it's the fact that the light is being confined to the forward cap. So, physical interpretation, kappa Kr, is the light only gets in to there, right? And so this basically is dark. So the rainbow and the glory, for instance, can the rainbow happen? We all know that there's an optical array explanation of the rainbow where the light comes in, refracts, bounces what comes out, and we get dispersion between the colors, right? So there's the rainbow, right? Red, and blue. The blue refracts more, right? But now if it's all getting absorbed before it gets in, we're going to lose the rainbow, the secondary rainbow. The backscattering has a lot to do with a combination of rays reflecting off the back surface as well, so the glory's gone. I've explained everything on the other side of 90. The hump itself, I'm not so sure. And that's where we concluded much of our discussion last time. I left my clicker over here. Let's back up a little bit. Well, maybe this is good enough. You might recall that I have a hypothesis that the scattering can be described as two-dimensional diffraction plus three-dimensional diffraction. Remember that? And since the three-dimensional diffraction has a Guénier regime at larger Q, it must be smaller. And it might be related to some sort of hot spot, quote unquote, at the back of the particle. So if you can't get any light to the back of the particle, that hypothesis would say the hump should disappear. So at least we have a consistent explanation, but it's still tentative. So that's where we are right now, is trying to describe why the hump and the other things disappear.
So a lot of that's based on, the hotspot's based on the geometry.
Yeah.
So get needs for, say, if that's particle, I don't know
Well,
if you get that big for simulations.
so one of the things we don't understand yet is that for all kinds of shapes, there's enhanced backscattering. And both glories and quasi-rainbows of some sort. Now, I don't think anybody's ever been in a desert windstorm and seen a rainbow when the sun's shining behind them or anything like that. But there is, in all these shapes, there's this little peak. And we have yet to study them in detail. Obviously, I want to do that too, right? And we would do T-matrix and DDA calculations on weird shapes. We'd go back there and take a look. And you know how I am, you know more than anybody in this room. We would systematically change size and refractive index and look for patterns. That would be the program. And any of you can do that too, because me calculators are available on the internet. And who knows, you might find some really neat things. Yes. Yes, when people model dust, they'll often put roughness, surface roughness on them. Or for instance, ice crystals. We just published a paper a couple months ago in collaboration with Ping Yang at Texas A&M. Ping had a bunch of ice crystal data, and some of the crystals had flat surfaces, but he also roughened the surfaces to different degrees. And the roughening didn't make a whole lot of difference with regard to our analysis. But it's important to say that we have concentrated on all of this and not paid much attention to that. And you might say that's a bit of an irony. Well, you might say it's a Q-space prejudice, right? Look at all of this, and there's only that. But if in theta space, right, there's 90 degrees. So in theta space, we're ignoring half of the functionality. And we really need to get back to the other half. Well, one slide on the ripples. Right? You can kind of see it coming here. Here's a 1 micron particle. See the ripples? Next is 3, next is 10. Oh, they're getting closer together with size, right? Turns out those ripples are spaced by lambda over the diameter. That's a nice result. There they are. There's an example. This drop was 23 microns in diameter. 23 divided into a half of a micron is what, 1/45th or something like that? 1/45th of a radian is what, 1.3 degrees, right? 60 degrees in a radian. You can see all the numbers working out up here, all right? And so if you do have a monodispersed aerosol, if you do have a single particle, and if you do want to know the size, one way to get the size independent of the refractive index is to count the ripples. Now, it's got to be a big particle, so you can have ripples, right? So that's a nice thing to remember. Forward scattering. Maybe I'll back up again, check my time, too. From this point of view, forward scattering just looks like some needle, at the beginning. But, of course, it's not. If you get into small enough angles, it's constant. And that's an important thing to recognize, and I'm trying to demonstrate with this. This is remember that white colloid and the blue colloid I had? Yeah, we shined the laser through the white colloid and went over on the wall and took this picture. So you can see the laser beam, but you can also see this uniform scattering in the forward direction. And the angle here, right there, is where QR equals to 1, so that's approximately lambda over d. There's your Gounier regime. It gets dark real quick. Why? Well, it's fallen off with at least the squared power of q and maybe even the fourth power of q, or the cube power, but it's fallen off quickly. One of my, all my students, so I teach Physics 101 to non-majors one semester, and then I teach astronomy to non-majors the other. And they all know that I walk my dogs every night around 9 or 9:30, which quite often is dark, except in the depths of the winter, in the summer, but I don't teach in the summer. And so I'll often be talking about, I saw the moon last night, and blah, blah, blah. But here's a lunar corona. And really, this is the forward scattering again. The light's scattering off the droplets in those clouds, and the scattering angle here, the moon's a 1/2 degree in diameter, so the scattering angle here is 1/4 of a degree. Here the scattering angle is 1 degree. Here the scattering angle is 2 degrees. You see, so that's that forward scattering lobe again. And I do this because I want you to watch for it too. You don't want to totally forget the beauty of nature.
I want to say it was a month or two ago, I thought I saw it from an orange haze. Is that something right? It was a colored haze.
Maybe it was close to the horizon and you're getting Rayleigh scattering through the air as well. Be my first guess. Notice can we kill the lights a little bit? Oh, he's going to have to come clear. Is there a switch I should? There's a little bit of red. Can you see the red?
Yeah, I see that, but it's only around the rim here.
Well, yeah, but let's remember the diffraction angle for red light is going to be slightly bigger than the diffraction angle for the blue light, and that's what's happening. And if we get the lights off the screen a little bit, there we go. Isn't that a pretty picture? So we'll keep them down for a little while. My neighbors love me because I take such good care of my lawn. This is my lawn many springs ago, and you can see the daffodils have seeded out, or not the daffodils, but the dandelions have seeded out. It's early some morning. The street runs east and west. I'm looking east, and you can see the reflection. The sun's off here in the northeast, of course, so it's probably June or something. And the point I'm trying to make is lots of forward scattering from the seed tops. Now I'm going to turn around and put my back to the sun, and you can see my shadow, right? Notice how difficult it is to see the seed tops now. So I'll go back. See the difference? So you can see this in lots of phenomena when you're walking around. A friend of mine, after I gave a talk like this, or I put this in one of my talks in our weekly seminar series back at Kansas State, the Condensed Matter Seminar Series. And Brett Flanders, who's another bicyclist, he said he was out cycling into the sun one evening, and a coyote ran in front of him and ran across a plowed field and kicked up dust, and the dust had all this forward scattering. So keep your eyes open while you're out with nature. Now, this is one of my favorite videos. That's my daughter, Hallie. She's probably about 10 years old, and she's standing outside for some reason. The sun's shining, but with an umbrella over her head. And she's thinking, my weird physicist father, now what the heck is he doing? And I wasn't able to embed this, so I'm going to bail out and go to my desktop for a moment. Earth calling space, there we go. Lens show, minimize. And as soon as I click on this thing, the video is going to start to run. So I'm walking around her, I tell her to smile, she gives me that little shit-eating grin of hers. And son of a gun, it's raining. See the sun off to the side? And then I'm going to walk back. And now you can't see the raindrops. Intense forward scattering. So the next time you're outside with the sun shining and it's raining, sure, look away from the sun to see the rainbow, but look into the sun and away from the sun and see if the great difference between the scattering due to these large particles in the forward direction. Orders of magnitude bigger. I like that. It's one of my favorites. Okay.
That makes like satellite retrieval and stuff like that kind of even complicates it more, right? You're at 180 degrees.
Okay, good. Let's see. All right. Total cross-section. Similar to the forward scattering, which is very strong and dominant. Here's the Rayleigh regime, strong function of the index refraction, causing orders of magnitude change, although I'm putting in some rather unrealistic indices of refraction, at least if you're an aerosol scientist. Now, colloid scientists sometimes have the particle nearly matching the medium, and you get these small values. But here for us aerosol people, 133 to 1.8, these three right here. But there's your standard Rayleigh functionality, crossing over to twice the geometric cross-section, and the refractive index being eliminated eventually. Turns out this crossover seems to be a little bit better described by 2 than 1, so I put rho primes of 2 in each case. You can see for the 2 extreme refractive indices. This was done for green light. So notice the sizes here, and this can kind of help you think on your feet. It does me. By the time you're at 1 micron and you've got a droplet of water, what's the total cross-section? 2 pi r squared. So, yeah, if you need something really accurate, pull out the Mie equations. But if you're just, say, planning an experiment and trying to figure out what the cross-section might be, 2 times the geometric cross-section. It's pretty simple. Keep that in mind. Okay. Now this slide is full of information, so I have to slow down with it. The total cross-section is when you integrate the differential cross-section over the solid angle. And of course the solid angle includes a phi integral from 0 to 2 pi, and it includes a theta angle, which is usually 0 to 180 degrees. That's your scattering angle there, 0 to 180. But what if you limit it to some partial angle? So we developed, notice this has just been submitted, so we call this the partial. Notice that's the partial derivative sign, although it's not really a derivative, but it means partial. So we define the partial scattering cross-section with this integral, and then conceptually it's just this. We're just looking at so much of the forward direction, and we can vary how much we're encompassing with theta. So then over here, we're going to plot it. Below, I've got the differential cross-section. This is just the Rayleigh scatter, or it's the scattering Rayleigh normalized again. That's QR. These are our Q space plots. There's the forward scattering lobe, Gounier, some -3, the hump, et cetera, et cetera. But then up here, on the same scale of QR, we're doing this integral. So we're increasing our scattering angle, and we're getting more and more cross-section. Notice this is normalized by the total cross-section. So we're coming up, coming up, coming up, and then it rounds off at about 50%. Where does it round off? Well, it rounds off where QR equals pi, which works out to be theta equals lambda over the diameter. So what I'm trying to say is you got this scattering going on, and as you start including more and more in the cross-section, right at the diffraction angle of lambda over d, you've got half the light. Then it pauses for a while. See that? Doesn't do anything for a while. And then, boop, it comes up to get the other half with the hump. Son of a gun. Isn't that cool? This is so much fun, you know. It really is. So the hump, and then to test the hump, so this is the scattering cross-section normalized by the total. We went to the efficiency. And the efficiency is the scattering cross-section divided by the geometric cross-section. And of course, the extinction paradox leads to 2 for large particles. Here's a radius of 20 microns. So we're looking at the efficiency now. And again, it shoots up to about 1, right, which is half the total. Then it goes up to 2 with the hump. And then we kill the hump with kappa KR. And sure enough, that second half dies too, right? And where did the second half go? It became absorption, right? So now you can see this interplay of scattering and absorption, and it's the hump that's, you might say, the arbitrator, the negotiator between the two. So that's pretty cool. So we submitted that. It got rejected 2 days ago. Anybody here Rodney Dangerfield? Yeah, I can't get no respect. I feel that way sometimes. So what the heck? We'll try another journal. Still, I mean, this is fun. I just think that's the coolest thing. So, I mean, we've only known about the hump for a year, and now we're doing this, so that's pretty cool. But it's true, whether the journal rejected this or not. There's no doubt about these results. Well, okay, so I've got about 10 or 15 minutes. So much of these functionalities appear in irregularly shaped particles too. So here we go. This was an important paper for me. Matter of fact, it was like a 3-page note back in 13. There's this great data set by the Amsterdam Granada data set. It occurs to me there's a camera watching me and they're getting the back of my head, but what the heck. These guys, Havenier ran it, but he was the professor, but Hesser Volten and Olga Munoz did this, and Munoz has taken it on since then in Granada. And they've taken all these desert dusts and Martian analogs and volcanic ashes, and they've blown aerosols through their detector, and they've scattered light from 5 or 3 degrees out to 170 degrees, and made all these fantastic measurements. They stored away their data. It's online, available, and they've plotted them all in all their papers, and of course they plot it linear theta, and they get these sweeping curves which are totally nondescript. That's the point. And so for some reason I thought, gee, I wonder if I plotted that logarithmically, what would happen? And son of a gun, it's a power law. And with there, remember we were talking? With a little bit of enhanced backscattering, right? Now there's no rainbow in there, and it's probably not even a glory, but it's enhanced nevertheless, and that's an unexplored area. Don't ask me, cool it. Don't you dare ask me what's going on back there, because I don't know, okay? But maybe we'll figure it out. Okay? We plan on figuring it out. So then, that won an NSF grant for us, thank goodness, and Heinsohn number 1, this is Heinsohn number 2, she got the whole doggone Amsterdam Granada data set and plotted them all, and they're all linear. Here's just a couple examples. Notice as few of them curve off a Gounier regime, right? Most of them do not curve off, and now we know that as marvelous as their data set is, they didn't get to small enough angles. They didn't get a Gounier regime. And that's a lesson to you, too. It's not 90, 80, 70, 60, 10, 0. I mean, in many ways, it's 99, 9/10, 0.09. I mean, that's too big of a jump. But you think logarithmically. There's a lot going on down there. And in many ways, too. I mean, get the boys and girls who try to get to absolute zero, right? 10 millikelvin, 1 millikelvin, 1/10 of a millikelvin, they're never going to get there. But if you can make an order of magnitude change, that's extremely important. So this was important to us, obviously. But also there's some systematic, I mean, what about the exponents? Here they're up in the 2s. Here they're down in the 1/6s. Are these fractal aggregates? That's certainly one thing. Well, but there's a picture of them. Those are not fractal aggregates. So we've done our own experiments. Again, Yuli's done this work too. She built this apparatus. We can scatter from 3/10 of a degree out to about 10 degrees with one of our detectors. And then a side detector, we can go from about 15 degrees to 150 degrees. So that gives us a good range of Q. And her first experiments were with sort of a classic powder aerosol, Arizona road dust. And you can see again, we get power laws, a slight enhanced backscattering, a Gounier regime. They're about 3 microns in size, and quantified power laws. And now to kind of speed up, a fellow named Zubko has done calculations off in Finland. These are calculations on these irregular spheres, and you did the analysis on this, right? Yeah. I always put Wildos back behind me. I never give him proper credit. But it's interesting. First of all, Zubko did this, but Will just took his data and Fourier transformed them. This is an important step. The diffraction limit, right? If you were diffracting, you'd get a Gounier, a forward scattering, and you get -4. But then when you turn on the refractive indices, 131, that would be ice, 1.5, et cetera, et cetera. At that time, we didn't know about kappa KR when we did this work. But now there's this kind of a Ripley structure, but we're still getting power laws. Justin Maum, who's with me still, 2016 paper. Gaussian random spheres, we get power laws. Will, if he ever gets off his butt and finishes this paper in preparation, has done thickened percolation clusters. I won't describe exactly what they are, but you can see one here. Power laws. And then Yuli, Heinsohn number 1, put it all together, and here's an empirical relationship. Rho prime, here's 1. If you're below 1, -4 diffraction from a 3-dimensional object with a 2-dimensional surface. right? But our data, some other data, all the Amsterdam data are on here. There's this trend with rho prime. They all sort of hang together, and we don't know why. However, notice I put a box. The fractal aggregates are here. They've got typically around 1/8 for the exponent, but they're rho prime less than 1. They're diffraction. Here is my single fractal aggregate slide. You might think me, being the guy who's worked on fractal aggregates for half my life, would have more slides on it, but this is enough for us right now. I've got a couple pictures, soot and a titania aggregate. You do scattering, you get forward scattering, Gounier, you get a power law regime. There's your fractal dimension, because twice dm minus ds, where dm equals ds equals 1.75, yields that. Why does diffraction work for soot with the very large and real and imaginary parts? Titania, you might know, is 2.6 for a refractive index. Why does it work? Well, it's because the stuff is spread out all over the place. It's fluffy. And so the effective fractal refractive index, and better yet, the effective Lorentz factor, is that of the monomers, but times the volume fraction. And the volume fraction in these things is very small. And in fact, if the fractal dimension is less than 2, the bigger the aggregate, the smaller rho prime gets. So that pushes us deep into the diffraction regime, or as the literature wouldn't call this diffraction, they would call it the Rayleigh-Debye-Ganz regime. So that explains that, but then there's a realization that we hadn't, this work led us to, and I'm trying to give it here. So I repeat myself, when we're at rho prime less than 1, diffraction occurs, and then we expect this functionality in the power law regime with these. And of course, now we find empirically spheres, dust, Gaussian random spheres, etc., Zubko's perturbed spheres, they're not fractal in any manner. They're all three-dimensional with mass scaling, and they're all two-dimensional with surface scaling, and so that's why you get the 4. Fractals are different, right? So once we had spheres and irregularly shaped particles. Now I contend we have spheres and 2 types of irregularly shaped particles. So we're making some progress. I'm very near the end, so be patient with me. It's a minute till the hour. Ice crystals. We just did this. You can see this is published. A bunch of these papers were published in 16. So here's this is called a Droxel. Look at that sucker. Well, he calculated the scattering. Let's do the forward scattering first, because it's a little simpler. We normalized it by the Rayleigh cross-section for such a thing, and that's where Justin Malm came in with the idea of trying to generalize Rayleigh scattering for non-spherical shapes, and non-elliptical shapes, I should say, as well. And you can see that it's coming up. Here's 1, so we don't have much in the Rayleigh regime, but it bounces around and it levels off at 1. Before he generalized it, it was spread out all over the place. Notice there's these numbers are smooth and different degrees of surface roughness. So they're about the same. What the heck is this? Well, Ping, notice this, it's a huge rho prime. Ping thinks that's a calculational error. So it is probably not indicative of what's really happening.
He's using some kind of weird algorithm in that range, right? He's not doing like a DBA or a T-matrix, right?
I think it's an IGOM, integrated geometric optics.
Ray tracing.
Yeah, and he says don't trust those data. So he's the expert. So this is looking a lot like spherical particles. Let's go further over here. Now, we got 3 different rho primes. Again, forward scattering, curve over at QR equivalent now of 1, Goonie A, and then this, see that, 9 QR equivalent to 9? That's what a sphere does. Remember the 9, even the 9, right, as low as the 4th. And son of a gun, that sucker comes out and sort of touches on. This falls off. Remember, we're Rayleigh normalizing, so as the particle gets bigger, more refractive, it falls relative to Rayleigh, as implied here. Goonie A stays where it is, and look at that, there's a bit of a -3, right, a hint of a -3, and notice the hump, so there's a hint of -2. Now, you're proper to accuse me to, I might be overinterpreting the data. I mean, we don't have orders of magnitude of Q space here and so on, but there are indications that these things look a lot like spheres, and notice they don't look like the dusts. And I totally frustrated me. I'm blank on propositions on what could be happening there. Well, not totally blank, I always have some guess. Look at this. I threw this in today. It's not in the slides, forgive me. But I realized, oh my gosh, this is for a column, an ice column. We've got 2 different ones. The L to A ratio, here's an L to A ratio of 1.4, so this is pretty chunky, right? Kind of like a drum. But here's an L to A ratio of 10, so this is more like a pencil, right? One of those hexagonal shaped pencils. All right. Let's look at one at a time. Let's look at the chunky one. So it's right here. There's a Goonie A regime. It comes down. And then, see this? It comes out. There's a hump. Now, depending upon the surface roughness, if it's not rough, the hump is a spike. It looks like a reflection or something. But when we screw up the reflection with surface roughness, it becomes a hump. Now, yeah, so this complex slide. Kappa KR is 0 are these gray ones with the hump. But there's Kappa KR of 20. The hump is gone. Isn't that cool? So similar, and notice even though we got Kappa KR of 20, this stuff stayed the same. It's only the hump and, of course, the enhanced backscattering that disappeared. So there's a lot of analogy there to spheres. Now let's go over to the pencils, the ones that are long and skinny. That's the darker ones. And again, similarity to spheres, but I also want to point out, see this regime, and then another curve over? It's got 2 Goonie A regimes. Isn't that nice? 2 Goonie A regimes. So if you're ever messing around with really anisotropic things, I mean, that's a 10-to-1 ratio. What's this, maybe 6-to-1 or something? But if we had a whole bunch of these and you were scattering, you might look in that forward and you might be able to pick up both sizes. You might also recall that I gave you an assignment to use that crazy scaling analysis of mine with those Q regions and try to figure out what a rod would do. If you do that, you'll get 2 Goonie A regimes with a slope of 1. Notice the size of these decades? A little bit smaller here than there. That's got a slope of 1. So it agrees with the scaling analysis problem that I gave you. And then it crosses over to 4. So finally, if you want, I've got 2 slides on scattering. This is our small angle scattering apparatus that we've been using for at least 10 years now. This is the apparatus that we used. You can see the 03s and 04s, Kim et al., Dabadell, when we studied superaggregate formation. we needed the very small angles. We had a key ray diagram here is right there, pi. I want you to look at this carefully because your ray diagram doesn't show this. Those lines are parallel. They're at the same scattering angle, but they focus, because they're parallel, one focal distance behind the lens. And that's what makes this plane the Fourier plane. Do you know any Fourier optics? Okay. If you get Hecht's book on optics, well-known textbook, he's got a chapter on Fourier optics. Read the chapter. It's really cool. Fourier optics is really cool. And it boils down to the fact that any object here, you can put it anywhere, but one focal distance behind the lens will be the Fourier transform of that object. So, and that's what we want to do, right? So it comes back to why I started off on Monday talking about Fourier transforms. Although I'm not trying to imply that this ray is bending for some mysterious reason, what I am trying to say, though, is that there's this Fourier image right there of whatever's there, and we want to image that onto our detector. So all this lens is doing is taking that and putting it here, and then that's what we get. We get the Fourier transform. Notice the wave vector. Notice our smallest q. It's at 2 times 10 to the squared inverse centimeters. Well, if you invert 10 squared, you get 1/100 of a centimeter, which is 100 microns. So we've gotten the length scales of 50 microns, okay, which is really humongous. And that's how we could see these super aggregates. Then I think this is my last slide. Yes, it is. This is the apparatus Uli built that I described earlier. And I put some angles on there for you just to give you some idea. The smallest angles in the Amsterdam Granada group were 3 degrees. Most of their day was at 5. We have a proposal pending right now to put that 512 channel detector in here and get to really tiny angles. We're also going to look in the back direction. We're going to look in every direction we possibly can think of. So that's it. Any questions?
Sir, in this current setup, I'm curious about the force scattering in smaller angle. Is that going to be limited by the size of the beam snout over there?
Yeah. I might back up one. That's crucial, of course. So you can see we use a tiny mirror. That sort of suggests something like a mirror, but what it is, it's a drill bit, which you can get in various sizes, of course. And we just cut it off at a 45-degree angle, and since it's such good steel, we can polish it and it reflects very well. And of course, we want to get it as small as possible so that we can get angles out there. You can see our data, though, are pretty good, right? These are leveling off. In some of our data, we'll get a downward dip because there's correlations between the particles, the aggregates that are forming. So, yeah, this is crucial right here, and you got to develop an experimental sense for how to place it, and also typically what we'll do is put a single slit here as our calibration, and you can buy these slits, 5, 10 micron type of thing, and calibrate with that.
I would like to think the size of the beam snout happens to be larger than the diameter of the beam.
Yeah.
So the force scattering angle, how small the beam is also determined by the...
Yes, it is. Notice the beam comes in, goes through the Fourier lens, and fortunately, the beam's getting focused right there. So we've narrowed the beam. And that helps us as well. I I forget what this smallest q corresponds to. Oh, there it is. So this smallest q corresponds to 8/100ths of a degree. And so the next one is probably 16/100ths and 24/100ths and so on, working their way out. Yeah. And it would be hard to do better. I should, as I did in bold, give credit to this guy Ferry, whom I've never met, but he published this paper with this diagram in it. And when I saw the paper, I saw a real opportunity in aerosol science, and so built one and took advantage of that.
What's the difference, this one, like, compared to the one in our demolition, like, you say, the X-ray?
Oh, like with x-rays? I'm not entirely sure. When I think of x-ray scattering, I think of much greater distances, right? So, and I don't think they do any Fourier planes. They just scatter and collect the stuff. So this whole thing, I mean, you know, I guess you can see how old this slide is. This is back when I was using an argon ion laser, which is, of course, that big, right? I hadn't realized that till just now. But it's a good diagram nevertheless. But right now, although my argon ion laser is still operational, we don't use it. I go in and hug it every once in a while because it was my pride and joy many years ago. I once owned 3 argon ion lasers. I take some pride in that. But now, of course, you get these little bricks, right, that emit light, 300 milliwatts of 532 or something like that. And we've got a couple of those. And so that's, you know, centimeters in size. This lens is probably 50 centimeters in diameter with probably about 50 millimeters in diameter, 100 millimeter focal length. This is a longer focal length lens because we could put the detector right there, but you can't get a big enough detector. So you have to demagnify it to get it onto the detector. This is a linear array. We've screwed around with two-dimensional arrays. In the forward direction, don't really gain that much with 2 dimensions, really. So linear arrays are just fine. Show you the other apparatus. It's very similar in the forward direction. I'm not sure why we're showing rays like that, but we are. This is a little tricky, but Yuli is extremely capable. This is an elliptical mirror, so there's one focal point and there's the other, which we spatially filter, collimate. These would be polarizers or wave plates, and let that fall on a 16-channel array. We have to calibrate these two against each other so there's no mismatch. You can kind of see where the break is. And we do that by we put a mirror in, bring it over, shine it at another angle, so now their angles are different and the 2 angular ranges overlap with each other and we can calibrate them against each other. So Yuli will be here in a year and a half when I let her go. She'll be here, golly, about a month from now. It's always been December, but now since it's the 11th of November, what is the date that she's planning on coming? Huh?
17th, we all shut down that week. And then we're going to my grandparents for Christmas the 19th, so that's going to be fun.
Yeah, so you're going to have another stimulating colleague. Yuli's just a marvelous person. She's, yeah, an experimentalist, hardcore. Yeah, very capable.
The A stimulating colleague, probably not that he's theorists over here. So you got all this, like you looked at all these data from all these irregular shapes, look at the phase angle. Have you tried to do what Justin did with the spheres and look at where the extinction, where the scattering extinction is happening? Do that integral, that partial integral, see like.
Oh, with different shapes? No, That's on our agenda. You know, if I could clone you, if I could clone Justin, I'd have all these guys making calculations and testing things out. But I lost my NSF grant, so why am I laughing? I have no idea.
Also, it's interesting that there's still, like, if you look at it, at the angle where the sphere, the extinction's flat, if you look at an angle, you still see light. What's going on with that? Is it not?
So I think I know what you're talking about. Let's just back up. Back to the partial cross-section, right? So you're saying what's going on in here?
It's like you're gaining no
It's a,
scattering extinction, but there's still scattered intensity there.
well, yeah, it pauses for a while. It's just the best way to say it. And then it picks up again. Now, let's remember in angle space, remember this was like 5 degrees right here. And this is a whole bunch of degrees from 5 to 90, right? So had I plotted this linear, this would look like western Kansas, just a long, slow slope up to the Rockies, right? But plotting it this way, it looks significant. Are we lying with our graphs? I don't think so. This is one way to look at it. And of course, the fact that this hump changes so dramatically with kappa KR and then corresponding changes in the scattering and absorption puts some viability to looking at it this way instead of with the linear graph. But, you know, I think in our paper, I know in our paper, we did the same thing with theta linear. And then you see it, boop, pop up, and then screw around and come up and level off. Yeah. But they're still separated ever so slightly.
And maybe that just washes it into regular shape. It still has to go to 2, right? Doesn't matter if you're a sphere.
Yeah, you got to get to 2, and at least if there's no absorption. Of course, as this comes down, the absorption is filling in to keep the extinction at 2. Does everybody know what the extinction paradox is? You gave me this curious look. The extinction paradox is the fact that a large particle, like my fist, when light falls on it, twice the geometric cross-section is eliminated from the beam. You would think, just by shadows, that only one geometric cross-section gets eliminated. Now, in the near field, it is just one. This is a far field type of thing, so you're going to have to do 2 or 3 orders of magnitude down, you know, the size of my fist to get into far field. The canonical explanation is there's both a shadow and diffraction around the edge. And recently, not so recently, but a few years ago, Matt Berg and I showed that's wrong. We have another explanation wherein, remember how we put an incident wave in and all the electrons started to oscillate and then that changed things? Well, when all those electrons start to oscillate, they kill the incident wave inside and make a different wave, but they continue to kill it behind the particle. That's the origin of the shadow. So the Ewald-Acine wave that's generated from the oscillating electrons is 180 degrees out of phase with the incident wave, which just goes right through the particle, but gets extinguished by that Ewald-Acine wave. That Ewald-Acine wave keeps propagating and it starts spreading because it's a wave. Okay? And hence it can't kill the shadow anymore, or can't kill the incident wave anymore. And when it spreads out there, you've lost both, you've got both the diffraction and the fact that you lost light. I'm not explaining this very well. Well, with this, I'm writing another paper, and I've asked Berg to join me on this. So, and the description I just gave you, how the extinction wave goes to infinity and looks like diffraction. I'm not saying this very well, but maybe I'll say this that I'm confident in saying. The concept of how an obstacle diffracts is often talked about. The light comes across the surface and diffracts into the shadow. That is wrong. What really happens is the light goes completely through the particle, and the incident wave is always there. But the secondary waves that come from the particle, when they first come out, are 180 degrees out of phase with that incident wave that's always there, destroys it and causes the shadow. But that wave keeps propagating and spreads out, and that's the diffraction in the far field. Can you turn up the lights? Oh, up here, is there some button I can push?
Hit lecture. Left panel.
Left
Lecture.
panel, lecture. Good. So the canonical view, the waves come in, they get chopped off. Let's draw the shadow. There they are, chopped off. But with time, they start to slop in to the shadow, like so. And then in the far field, you get the single slit diffraction pattern due to that. So we're claiming that's not the case. We're claiming that the incident wave comes in, keeps right on going. But secondary waves are generated that by the dashed line I'm trying to indicate are 180 degrees out of phase with the incident wave. So this adds up to 0. In the far field, notice the incident wave is broader than the secondary wave. Who diffracts the most? The smaller incident wave. So in the far field, this guy is cranking along. Let's scale it down a little bit. So this guy is spreading out a little bit. Right? But this guy is spread out more. Like so. And how big was it originally? The size of the particle. So it looks like it came through a hole, the size of the particle. There's your Babinett principle. And this becomes single slit diffraction pattern that we see in the far field. So that's the proper way to understand diffraction.
So that's going through a particle, but if you're going through a hole, how is it?
That's harder. That's harder. So I won't try to draw that.
Is the light actually penetrating everything?
Yes, it's going through the screen, and the whole screen is emitting secondary waves.
Can you isolate this experimentally, where you can just get those secondary waves out there somehow? I guess you got.
I don't know. I don't know if you can tell one wave from another.
You can look at pulse lasers
catch one yeah, yeah.
Maybe not understanding correctly, but if you use a screen material with a very high complex to factor index, wouldn't you prevent the forward entry? If there's a lot of absorption.
So this is a screen with a hole in it,
Yeah,
and you want to maybe make a mirrored screen or something like that.
so would it change the pattern then?
Well, the way you explained the mirror is that that mirrored surface emits a secondary wave in both directions, and in the forward direction it cancels the incident wave, and hence there's nothing back there to create the shaft. Backward direction, it's the reflection you see, perhaps because it's so shiny and metallic.
But in that case, a mirror with a hole, shouldn't the single slit pattern be different? Because if the forward of the mirror itself is being cancelled, then you only have the hole.
That first beam of light though is not seen. Remember, you're looking at a unit scale. On the light scale, it just sees atoms and fields. So that light beam is going to penetrate all that stuff before all the electrons and stuff sort themselves out and reinvent to get the mirror.
I'm just looking the forward direction. So you said that if it's a single hole, if it's a hole in the screen.
Hole in a
Then
screen.
you have the light going through the hole and interacting with the secondary emission from the screen. That's what creates this pattern.
Right.
But if the screen material is made up of a mirror, which itself has light penetrating through it and a secondary wave which cancels the original, then it can't interact with the light going through the hole, right? So wouldn't the pattern then be different?
Well, I think it's the light that survives either gets absorbed or reflected. The transmission is still the same.
As it is
Cancel
just
away.
a single screen.
Yeah, we do the same, but then what happens from here is it getting absorbed or reflected.
So I'll caution you that I probably will not be successful in remembering our arguments. But if we have a screen, let's just try to draw it, at least get something on paper with a hole. So this is now a physical screen, not a bunch of waves. So the incident waves come in and go right through it. Now this thing is radiating, and one can imagine that the radiation initially right here and 180 degrees out of phase. It must be because it's dark back there. Notice this is still here. That might be enough, right? Given the semi-infinite nature of this, seems to me these can't do anything else but to stay, I mean, they're never far enough away from this. You probably know in electrostatics, if you charge a plate, the field is constant, independent of the distance, as long as it's a semi-infinite plate, right? So I'm thinking out loud here. So it seems to me the only thing that can happen is that this wave exists. So let's now let the red and the green interfere with each other. Right? And there we go. That's going to diffract and cause the single slit diffraction pattern.
Well, what's happening on the other side if that screen was a dark screen or a mirror?
Well, if it's a dark screen, then some of the radiation is getting absorbed and turned into something else. If it's a mirror, then there's these. So the red is the secondary radiation doing that. Well, now let's remember the greens are going one way and the reds are going the other way here. So here we've got them propagating together, here we got them anti-propagating. So here you can have a steady state situation of interference and hence annihilation. Here you'll definitely get interference, but you're not going to pick it up because it's going to be beaten so fast at the attosecond scale that you're not going to detect it.
And if it's a dark screen, the oscillation is of the electrons doesn't emit anything. Well, it might emit a little that way, but it's going to get hammered fast.
So maybe now to redraw the obstacle, you may all draw a particle again. So here comes the incident wave. Here comes the secondary wave. And we get a shadow. Then a long ways away, the incident wave is diffracted a little bit, right? At some angle, lambda over beam waist, right? But the diameter of this particle is less than the beam waist. So this extinction wave, which caused the shadow, has now diffracted huge angles, relatively speaking, lambda over d. And, you know, most beams are maybe 100 microns in diameter, and most particles are 1 micron in diameter. So I'll make some sort of argument like that. And so this is what you see in the far field. See that what's falling, yeah, maybe that's another way to say it, kind of an interesting thought. With an obstacle, what's falling on the screen in the far field are waves that are not the original incident beam slipping around the side. They're waves radiating from the electrons in the particle. They have a different home. That's kind of neat. I hadn't thought of it that way before. Right, the incident wave had some electrons clear.